Okay, this is the sample of a practical assessment for the Applied Science course where you will have to do an investigation into the rate of cooling of an insulated conical flask. So you have to do a practical and gain some results in 1 hour. And this is the first section, section A. So you get given a little introduction, what the apparatus are, and a nice simple method. And as you can see, we're going to put some bubble wrap around a conical flask, fill it with some hot water, and measure the temperature change over time using a thermometer. Okay, so all that is detailed there. Now, first thing you need to do then is a quick risk assessment. So you need to identify the hazard, the risk, and the control measure. The hazard is something that could be harmful. So we could have scalding by hot water. So the risk is that you could spill it from the flask. A control measure then would be place the flask on a flat surface so it's unlikely to spill, and when you're adding the water, just take care that it does not tip over. Then you need to make a hypothesis for this experiment. A hypothesis is a scientific prediction. So I predict that as the temperature of the water in the flask will decrease with time. If I just said the temperature decreases with time, I'm not being very accurate there, and I'm not linking it as well as I should to this practical. Now you can see what we're going to be asked to do is to fill a conical flask to 3/4 full of water, measure the initial temperature, and then the temperature every minute for 15 minutes. So it's the temperature of the water that I think will decrease with time. So it's important that I mention water and not just say the temperature will go down. Okay, so you then have to construct a results table to put your results in. It's this nice simple method, there's no repeats, so I'm just simply going to have time in minutes. We're going to take the initial temperature at time 0, and then every minute for 15 minutes, and then I'm just going to measure the temperature of the water. It's important that you make sure the units are in the heading of the table. You do not need to put minutes in the columns, just simply in the table headings. And that's it. That's the end of the first hour. In the second hour, you will then have to do a section B, which is going to ask you some questions about the practical. Okay. Now, so it's the same investigation. First of all, ask you to identify the independent variable, the thing that was changing, the thing that you changed. And in this case, it was time. We measured the temperature over 15 minutes. The dependent variable is the thing that you actually measure, and of course this was our temperature. Then identify 2 variables other than the starting temperature that you controlled in order to compare your results with other groups. So they're telling you can't use this one. So the other ones you could use is the same volume of water, same thickness of bubble wrap, same type of bubble wrap, same material of the flask. Obviously they're all going to be glass conical flasks, but you could get plastic ones. But you only need 2, so I've just listed 4 that you could have chose. But the obvious ones are the same volume of water and the same sort of thickness of bubble wrap. Then you plot your graph. Now ignore this line at the bottom for a second, that's for a later question. But along the bottom, your x-axis is the independent variable, and we said this is time in minutes. Okay, so we're going to go from 0 all the way up to 15. Along your y-axis is your dependent variable, the thing that you measured. This was temperature in degrees Celsius. So both times make sure the units are there. The graph should be over half of the space that they've provided for you. And you can see this is a perfectly sized graph. So I plot my results and I do a line of best fit. Now, was your prediction in section A correct? Well, just take a look at the graph. Over time, the temperature decreased. So yes, as the temperature of the water decreased over time, yeah, the prediction was correct. Calculate the mean drop in temperature per minute. So per minute, how much is it on average dropping? What I need to do is either look at my graph or look at the table from the first section, section A, which will be provided back to you, so you'll have your results. I can see there's a temperature drop from, I believe, temperature drop of 49 degrees because we've gone from 92 down to 43 degrees Celsius. So a temperature drop of 49 degrees. Now, of course, this took place over 15 minutes, so 49 divided by 15 means that on average, the temperature is dropping 3.3 degrees Celsius per minute. Okay, it was actually 3.26, I just rounded it up to a sensible number. Now, add a line to the graph to show how you would expect the uninsulated flask to cool, and label the line uninsulated flask. So a conical flask with no bubble wrap around it, I'm thinking this would lose the heat much quicker. So I've drawn a line, same starting temperature, but the line is much lower than the line for the one with bubble wrap. So this is my uninsulated flask, and they're going to lose the water's going to lose its temperature much quicker. Explain the difference between the two lines. Well, there's going to be a steeper drop for the uninsulated flask because the heat will be lost quicker. Simple as that. Now, for every 1 degree Celsius drop in temperature of 1,000 centimeters cubed of water, 4.2 kilojoules of energy is transferred to the surroundings. Calculate the amount of energy transferred in joules when 250 centimeters cubed of water cools by 10 degrees Celsius. Right, so for 1,000, 4.2 is lost, but how much is lost for 250? Right, so 4.2, it says for every 1 degree drop, we lose 4.2 in 1,000, so 4.2 times 10, okay, because we're going to have a 10 degree drop, not 1. That gives us 42 kilojoules, okay? And at 1,000 centimeters cubed, this gives us 42,000, but of course, we're using a quarter of that, so I need to divide it by 4. Okay, so 42,000 divided by 4 will give me 10,500 joules in total. State 2 changes that would reduce the heat loss from the flask. Well, we could put some sort of insulation at the top of the flask to stop heat rising through the top. We could also cover the flask with some silver foil to reflect the heat back in, or add another layer of bubble wrap. Finally, you need to, here it asks us to write a plan describing how you would carry out an experiment to compare two different insulating materials to discover which one was more effective at preventing the heat loss. So we're not going to carry out this experiment, they just want us to plan it. So I'm going to copy the method we just seen. You make sure it's very similar. So we're going to wrap one flask in cotton wool and another in bubble wrap. There's my two different types of material. I'm going to use the same thickness for each. So I'm talking about how I'm going to make sure it's a fair test, what my control variables are. Step 2, fill both with the same volume of water from a recently boiled kettle. Okay, you could give the amount, but I'm simply emphasizing that it's the same, so that should be fine. Measure the initial temperature of the water in both flasks with a thermometer and start the stopwatch. Measure the temperature in each every minute for 15 minutes. I must show how I'm going to collect the data, okay, so I can compare the two. And then finally, I will compare the temperature drop in both. And what would I expect to see? Well, the best insulator would see a smaller drop in temperature. Okay, and that's it.